Hello, students. Today I am going to start off with the last topic of bonding, and that is giant covalent structures. They are also called macromolecules. First example is diamond, graphite, silica, which is also known as sand. These have giant covalent molecules with extremely large molecular lattices. All atoms are joined together by strong covalent bonds to give a giant three-dimensional lattice. These are very stable and have high melting points and boiling points. Now we come to the structure of diamond. Diamond is one of the allotropes of carbon. Allotropes are different forms of an element that have the same physical state but different chemical and physical properties. They exist in different structures. Other allotrope of carbon is graphite. Each carbon atom contained is covalently bonded to four other carbon atoms to form a tetrahedron, which in turn is bonded to four more carbon atoms to form three-dimensional structure. Now this I am talking about the structure of diamond. You can see the structure of diamond which I have drawn. You must practice drawing these structures. You can see easily that is it has a tetrahedron and a hexagon. All together they make a giant structure. It is difficult to break these bonds, covalent bonds. It is very hard. It is used for drilling, cutting edges of other tools. When well cut and polished becomes a valuable gemstone. It does not conduct electricity as its all four electrons are covalently bonded and there are no free electrons. Remember, electricity can only be conducted if the substances have free electrons or free ions. Now we come to the structure of graphite, the another allotrope of carbon. It is soft, slippery, fairly unreactive, and unlike diamond, good conductor of electricity. Being soft and slippery, can be used as dry lubricants. Having free electrons, it can conduct electricity, and when mixed with clay, it may make lead pencils. All the above properties are due to its structures. Each carbon atom is covalently bonded to three other carbon atoms, which in turn are bonded to three more carbon atoms, forming a continuous layer of hexagons. Each carbon atom has one outer electron that is not used in bonding, so it can move freely along the layers and said to be delocalized. Due to these electrons, graphite conduct electricity. Graphite is used as lubricant because layers of hexagons can slide over each other because of weak intermolecular forces of attraction between them. It has high melting point, boiling point because of strong covalent bonds and formation of continuous layer of hexagons. Now I have drawn the diagram, and you can easily see in the diagram that is carbon is covalently bonded to three atoms, other carbon atoms, and it is forming layer, and between layer with the dotted line I have mentioned weak intermolecular forces, and among these lines we have between these layers we have delocalized electrons which conduct electricity. Now we come to the structure of silicon dioxide, another example of a macromolecule. It has similar structure to diamond. The difference between them is that silica is made up of silicon atoms bonded to four oxygen atoms covalently, forming tetrahedrons and hexagons just like diamond. Is a repeated manner form giant structure. It has high melting point, boiling point because of strong covalent bonds. It does not conduct electricity because of no free electrons. All the outer electrons of silicon and oxygen are used for bonding. Now you can see the structure. The only difference between silicon and silica and diamond is that you can see that the larger atoms are of silicon and smaller are of oxygen. Silicon is forming a tetrahedron by joining bonding between four oxygen atoms, and oxygen have two bonds. Oxygen does not make more than two bonds. And on the other right hand side, I draw the simple structure which can mostly come into your exams, and you have to identify or you have to draw it. So now we come to, this was the end of our molecular structures, giant molecular structures. Now I come to yet another type of bonding, that is metallic bonding. A metallic bond is the force of attraction between positive metal ions and the sea of mobile electrons. Now, in order to study this, or in order to understand this definition, we need to study the structure of metal atoms. As we know that atoms which have 1, 2 or 3 electrons in their outer shell show the properties of metal, these electrons are easily lost, leaving metal atom positively charged. These electrons in metallic lattice become delocalized and move freely between the metal ions like a cloud of negative charge. This makes strong electrostatic attractions between the positive metal ions and delocalized negative electrons, forming a strong metallic bond. Now you can see I have drawn the structure diagram, and over here I have drawn the positive ions, that is metal ions, and outside with the blue dots I have drawn electrons which are showing the mobile electrons. Now you can see over here with, that is, it is unipositive charge. Metals can have 2 positive charge, 3 positive charge. So this I will discuss when I will talk about the metals. Now, physical properties of metals. First of all, they are good conductors of electricity. Mobile electrons allow the metal to conduct electricity. You can see I have drawn over here in a wire. When electricity is applied, it is connected to some circuit. From negative terminal, electrons start entering the wire and they move from left to the positive side and they leave to the other circuit. So this is how flow of electrons takes place. If there would have been no electrons in it, it will not conduct electricity. They are good conductors of heat. Heat energy is transferred easily by mobile electrons. Metals have high density, melting point, boiling point, because metal atoms are tightly packed and held together by strong metallic bonds. Now, metals are malleable. Malleable means they can be hammered into different shapes. Metals are ductile, which means they can be drawn into wires. When a force is applied to a metal, the layers can slide over each other through the sea of electrons, and metallic bond is not disrupted, and thus it can change the shape. So I have drawn the diagram. Left side, it is the metal before the force is applied. On the right side, it is the metal on which the force is being applied, and you can see the internal layer being slide slightly towards right. So this was all about the metallic bonding, and rest properties and structures of the metals we will discuss later on. Thank you.